Okay, starting Unit 3 for Honors Math 3. Polynomial functions and their graphs. 3.1, we're dealing with the degree of a polynomial and the end behavior for the curve. Okay, so what is the degree of a polynomial function? The degree is the highest power of x when it's multiplied out. Okay, and a polynomial function has the form it doesn't have to be p of x, but could be just y equals a sub n x to the nth power plus a sub n minus 1 times x to the n minus 1 power plus a sub n minus 2 times x to the n minus 2 plus keeps on doing that pattern until you get down to like a sub 2 times x to the second plus a sub 1 times x to the first. Now, if it's the first power, we don't really have to write the first power, plus a sub 0. Okay. Now, the a sub n's, those are real numbers. Could be integers, could be fractions, could be a radical. The exponents do have to be non-negative integers. Okay. So I guess we could go ahead and write that down. N is a non-negative integer. And a sub n cannot equal 0. Okay, so let's take a look at some examples of that. So let's say we have something like y equals 7x squared minus 4x plus 2. And we've got the leading coefficient. We've got the degree. And then we've got the end behavior we're going to talk about. Okay, so for this first one, the leading coefficient is the coefficient for the highest power of x. It's the a sub n effectively. So the leading coefficient here is 7. The degree of this function, it's all multiplied out, so the highest power of x is 2, so it's degree 2. And so when we have a positive leading coefficient and an even degree, the graph starts high and it ends high. So out to the left, it's high, and as we end out to the right, the graph is high. So it's kind of starting high, and it's ending high. Now, what it does in between, in the middle, that's something we're still going to get into. Okay, let's try another one of those. So number 2, let's say we have f of x equals 3 minus 2x minus x to the 5th. Okay, and the leading coefficient is -1. Now, in case you were thinking it's a 3, now you have to look for where the highest power of x is. So the highest power of x is the x to the 5th, and the coefficient of it is -1. The degree, then, is 5, because that's the highest power of x when it's all multiplied out. Now, this is an odd degree, and the leading coefficient is negative, and so this is, it starts high, and it ends low. Okay, so out to the left, it starts high, and as you go to the right, it ends low. Now, what happens in the middle, we're still going to get to there, but starts high, ends low. Okay, let's try this one. If we have g of x equals -8, of course, y equals -8, isn't that a horizontal line? Okay. So the leading coefficient is -8. The degree is 0, because it's -8 times x to the 0. And the end behavior, it's continuous. It's a horizontal line. And it's just maintaining elevation -8. So don't let something like that fool you. Fourth problem here. Y equals 2x squared times x squared minus 5 times x to the 3rd plus 4. Okay, now this one's at least a little bit tricky, because it's not multiplied out. Now, we could multiply it all the way out, but we don't really want to have to multiply it out, because all we really need to see is what the highest power of x looks like when we multiply it all the way out. So if we were to multiply these out, the ones in the parentheses, we'd have 1x squared times 1x to the 3rd. And so that would be 1x to the 5th, the highest power of x when we multiply the parentheses. And then if I multiply that times the 2x to the 2nd, the highest power of x, this is looking like y equals, it's going to be a positive 2x to the 7th plus a bunch of other stuff. Okay, now the other stuff is important, but not as far as the end term behavior goes, because we can determine the end term behavior based on the leading coefficient and the degree. So the leading coefficient is a positive 2. The degree for this function is 7. And so since the degree is odd and the leading coefficient is positive, then this one actually starts low and ends high. So out here to the left, it's coming from down low, and as you go to the right, it's going up high. In the middle, we're still getting to that. We don't have that right now. Okay, so now if you think about, because right now I haven't really explained why this one was high to high, why this one's high to low, and why this one is low to high, and so on. But if you think about some basic functions here, let's say we just think about y equals x. Really, really basic first degree polynomial. And it's going through the origin. And so since this one is odd degree and the leading coefficient is positive, this one is doing low and ending high. So low to high. Okay. If we did y equals x squared, the most basic second degree polynomial. Well, you know it's a parabola, vertex at the origin there. Okay. And so we can see this one starts high at the left and ends high on the right. So this one is high to high. Okay. We're trying to notice some patterns. That's where the power of math really is anyway. The power of math is noticing patterns and harnessing those so that we can use them in more complicated situations. Y equals x cubed. Okay. I don't know if we've really done anything quite like this before, but okay, picking up where we left off, the y equals x to the third. It's an odd degree. Its leading coefficient is positive. It does do a low to high. Okay, and let's squeeze one more on here. And so this is going to be, let's see, I didn't label this one. So this one was low to high. Okay, y equals x to the fourth. Noticing any patterns? You think this one was low to high. This one is high to high. This one is low to high. What do you think? Well, y equals x to the fourth. If we plug in some points, it is kind of a parabola. It's not actually a parabola. Parabolas are just degree 2. But it's fairly similar to a parabola. And this one is a high to high also. Okay, so predictions. Let's see. First degree, positive coefficient, low to high. Second degree, high to high. Third degree, these are all leading coefficients that have positive values, low to high. And fourth degree, high to high. So, what do you think fifth degree would be? Well, let's just go ahead and try one more. So y equals x to the fifth. And if we plugged in enough points, we would be getting something that looks like this. And so this is a low to high for the end-term behavior. Okay? I think we're ready to write down pattern at least for the positive leading coefficient. Okay? So, odd degree okay, and leading coefficient is positive, odd degree, leading coefficient is positive, sure looks like it's low to high, and that's what it is. We're going to get to the leading coefficient is negative. We're not quite there yet, but let's leave a spot for that. Odd degree, that's the odd degrees. Even degrees, so even degree, and leading coefficient is positive. Well, let's see, what do we have? We have high to high, high to high for x to the fourth, and x to the sixth is high to high. So high to high. And we need one more spot for even degree, and the leading coefficient is negative. Okay, now we're going to come back and do the negatives. We're going to do the exact same graphs. So what happens if I have y equals negative x? So leading coefficient is now negative. Well, we've done it. Doesn't it reflect across the x-axis? Okay, looks like it's high to low. High to low. And if we did y equals negative x squared, reflects across the x-axis. Low to low. And if we did y equals negative x cubed, reflects across the x-axis, it would be doing this, which is a high to low. And if I did y equals negative x to the fourth, now realize the negative does not have the power on it. It's negative 1 times x to the fourth. So it reflects across the x-axis, and it is a low to low. Low to low. Okay, y equals negative x to the fifth. Reflects across the x-axis, and it is a low to low. Okay, so odd degree, leading coefficient is negative, high to low, high to low, high to low, well, it's high to low. Even degrees, leading coefficient is negative, low to low, low to low, and if we did negative x to the sixth, it would also be low to low. So here is our little chart to keep track of all that. Okay? Continuing with the notes. There are, at most, n minus 1 direction changes, or changes of direction, for a polynomial of degree n. So there's one fewer change of direction than the degree, at most. There can be fewer. Let's take a look at an example of that. Let's say we had a graph, and my graph is doing something like this. And we're interested what we know about the degree, maybe even the leading coefficient. So for example, notice it starts high and ends high. So that should tell us that the degree does need to be even. But the function is decreasing, then it's increasing. So that means there was a direction change right there. And then it's decreasing again, so another direction change right there. And then finally, it's increasing again, so we had another change in direction. So 1, 2, 3 changes in direction. This polynomial is at least degree 4. Could be more. 4 matches up with the high to high. Since it is a high to high and it's an even degree, we also know that the leading coefficient would have to be positive. And so we can tell that sort of thing as well. It could be higher than degree 4, but it's at least degree 4. Let's write a sample polynomial, write a polynomial equation that satisfies on the left, f of x goes to positive infinity. On the right, f of x goes to negative infinity. Okay, so all I'm really giving you is just n-term behavior, and this is kind of very formal wording. But the fact that on the left it's way up high, and on the right it's going way down low. So this is a high to low. Since it's a high to low, it has to be odd degree, and the leading coefficient needs to be negative. So a possible equation y, or since it's talking about f of x, so f of x equals, really it's just any odd degree, so first degree, third degree, and the leading coefficient needs to be negative. So you could do something as simple as negative 7 x to the fifth. That would suffice. You could have something else. You could have plus x to the fourth minus 2. It's just the highest power of x does need to be an odd degree, and the leading coefficient does need to be negative. Doesn't really matter what the leading coefficient is as long as it's negative. Okay? So that's, you could come up with many other samples that would work with that. Here's a question for you. Does every polynomial function have to touch or cross the x-axis? Okay, think about that sort of thing. Well, maybe we should break it down a little bit. What about odd degrees? Okay, odd degree polynomials, it's either low to high or it's high to low. Wouldn't it have to cross the x-axis at least once? Yeah, so odd degree must cross at least one time. What about even degree? Even degree, remember, is either high to high or low to low. Would it have to touch or cross the x-axis if it's one of those two situations? Wouldn't have to. Does not have to touch or cross the x-axis. Excuse me. A possible sketch for that, if you think about it, how about just like a parabola that's the vertex is above the x-axis and it's going from high to high. There's an example of a polynomial function that does not have to cross the x-axis.